Very, very, very good morning to all of you, and let's have a quick comparison of the two important frameworks in quantum mechanics. What we have is uh, uh, we have Hilbert space, and then we have Fock space, and let's try to compare the uh, two formalisms that are basically executing uh, an action based on the vectorial nature of the state vectors that we are dealing with. So what will be the main motivation here is that we would like to have a comparison between the Hilbert space and the Fock space versus, in the framework of second quantization. Now, to introduce you, what's the aim of this short video is that we would like to explore some of the important differences between the Fock space and the Hilbert space. And the key, these two tools that are basically exonerated in the framework of quantum mechanics, they are basically a key to quantum mechanics and quantum field theory. Now, talking about the Hilbert space, in general, it's used in first quantization. The most popular framework for the Hilbert space is used in first quantization. And we have already talked about the first quantization where we basically treat our system with respect to a wave function. This Hilbert space has a range of state vectors in it, and what it does basically, it's a complete vector space where there always exists an inner product, and this inner product is already discussed. So this inner product is almost similar to the scalar product that we have in the conventional vector models. And the main purpose of Hilbert space is, what it does is basically it describes a single particle quantum state. Okay. Now, talking about the Fock space, to give you an overview of this space, it's used in second quantization, and it's constructed from a direct sum of the tensors. So you have tensors, and you add up the tensors. You add up the tensor products of the Hilbert spaces. So here we can see a connection between a Fock space. You can have a set of Hilbert spaces, and you, in a Fock space, when you want to develop a Fock space, it is to be constructed from a direct sum of the tensor products of these Hilbert spaces. So certainly the definition goes in a way that it's a formulation that describes the multi-particle quantum systems. Okay, now again, talking about the first quantization, quantum states are represented by the wave functions, and these wave functions live in a framework known as Hilbert space. And the operators that we have in first quantization, like position operator, energy operator, momentum operator, these operators act on these wave functions, and you have the examples of these operators as position and momentum operators. And again, talking about second quantization, what we do here is we have quantum states. These quantum states are described in terms of occupation numbers. And if you go to the first quantization, your quantum state is represented by a state vector. And here our quantum states are described in terms of what's called as occupation number. And we have those operators because here we have variable number of particles that we can deal in Fock space, which is not the case when you deal with an independent Hilbert space. The number of particles in an independent Hilbert space is constant. You cannot add a particle to Hilbert space, or you cannot remove a particle. But that's not the case when you talk about the Fock space. What you can do here is you can add a particle to your Fock space, and you can remove your particle to the Fock space using creation and annihilation operators. So these creation and annihilation operators act on this Fock space. But again, the number of the particles that will exist in this Fock space, this is going to remain same. But you can vary the number by adding a particle and removing a particle, so that the overall number of the particles does not change. So it is useful for variable particle number systems. So when we have a variable number of particles in a system, there we can think of exaggerating the use of this Fock space. Now, talking about the mathematical structure for Hilbert space, we have a state vector. It can be represented by a ket of psi, and this ket of psi will exist to have an inner product. So if you have the ket of psi and you have the bra of phi belonging to the same basis, you can have an inner product between these two vectors. But for Fock space, what we have sum of symmetrized or anti-symmetrized tensor products. This is the most important argument about the Fock space. What you can have in a Fock space is you can symmetrically have you can symmetrize your bosons, the framework of Bose-Einstein, or anti-symmetrize your fermions using the product of tensors. Now, Hilbert space, it's a single particle, or you can also say a fixed number of particles live in this Hilbert space. And talking about the Fock space, is a variable particle number space, and what you can do is you can create and annihilate the particles in the Fock space, which is not the case when you talk about Hilbert space, which is the basic framework for quantum mechanics in first quantization. Hilbert space, talking about the applications, quantum mechanics of single particles, and Fock space, the quantum field theory, and many-body physics and condensed matter physics. These are the fields that can be demonstrated using Fock space, and the quantum mechanics of single or fixed number of particles can be expressed in terms of the Hilbert space. So, talking about the advantages of Fock space, what it does, it handles indistinguishable particles easily. We're talking about indistinguishable particles, and supports particle number change naturally. You can grow the particle number, and you can descend the number of particles to your Fock space in the framework of Fock space. So it's more powerful. It's a more powerful tool for the domain of the modern physics problems. So to conclude this short video, in which I tried to make a brief comparison between the Hilbert space and the Fock space, the motivation was just to put up the basic state of difference. Even though they have a connection, a Fock space is connected to the Hilbert space. You can connect the two spaces. using tensorial mathematics, but it's I thought that it would be right to make an argument about the differences between the Hilbert space and the Fock space. So to conclude it, Hilbert space and Fock space, they are foundational to the quantum theoretical models. Their use depends on the physical scenario and the problem, the type of quantization we are interested in. So with this, I would like to thank you all. Thanks for watching. Okay, see you. Bye.